Good evening. This is our 12th lecture, and in the previous lecture, we have actually talked about the shapes of rigid particles. Now, we'll try to see the shape of fluid particles. Already, for one of the case, I have explained some of the shapes for fluid particles as well, and then we will try to see the governing laws. Already, we have discussed about the governing laws, but now we will try to see the more simplified versions of the governing laws for some specific flow situations, so that we can study the behavior of spherical particles present in different flow situations. Okay, so in terms of the first fluid particle shapes, I had told you about the sessile drop or sessile bubble or drop. Okay, so it means here I can have bubble as well as drop, both the systems present. So anything which is resting on the surface, flat surface, that we are calling as a sessile drop, and anything which is hanging from the surface, these we are calling as pendant shapes. And then something else was also there. If we have three phases which are interacting with each other, okay, and their density distribution is such that rho 1 is greater than rho 2 greater than rho 3, then we will be having the existence of particles something like this, which we are calling as floating particle. Okay, and ultimate point is that all these shapes which we are getting, these are nothing but coming from the balance of tangential as well as the normal forces which are acting on this particular interface. So this is nothing but interface which is segregating one fluid from the other fluid. So we mentioned that if tangential and normal forces are balanced at this interface, then we will be having one particular shape present. Okay, so if there is imbalance of the forces, then there will be, of course, change in the shape. Okay, and third important point I highlighted that all these hatched portion over here are nothing but representing the higher density, and the portion which is white, which is not provided by any other color, that is nothing but representing the lighter fluid. Okay, now I was explaining this particular equation, so let me again put it in a more simplified version. So typically, if you have any spherical drop or bubble, then typically within the drop or bubble I will be having some different pressure Pi, and outside this I will be having some other pressure P. Okay, and the difference of this Pi minus P is something which is balanced by the surface tension forces. Okay, so typically for a spherical drop or bubble, what we will be finding that if I take a plane in one plane, or if I take plane in any other transverse plane, then in both cases I will be having the same radius of curvature. Okay, so let me call this radius of curvature to be R naught. Okay, so if this is the situation, then simply my pressure drop will be equal to 2 sigma by R naught. So this is something which we are already knowing from our basic fluid mechanics. Okay, now what we have to do, we have to develop from this point. So what we are considering that all these shapes, whatever I am having, all these shapes are nothing but corresponding to the rest situation or stagnant situation. It means I don't have any sort of motion within the surrounding fluid as well as within the particle. Okay, so if all these shapes are corresponding to rest position, it means all these shapes must have pressure and surface forces balanced to each other. Okay, so in this scenario, what will be happening if I fix this particular point to be my origin? With reference to this origin, if I say my y coordinate is varying like this, okay, so ultimately whatever the outside pressure is there, so inside pressure is nothing but Pi and outside pressure is P. Is this point clear? And whenever I am talking about pressure variation within the particle, so hydrostatic pressure variation within the particle will be nothing but because of the density difference between the two particles and the height parallel to gravitational direction. Okay, so that's why this Pi minus P, This pressure I am just saying that it is coming because of the hydrostatic portion. So if it is coming because of the hydrostatic portion, so let me write Pi minus P as nothing but density of particle minus density of the surrounding fluid, okay, multiplied with G into Y. And what I have done over here, I am considering that my reference point to measure Y is nothing but at this central tip of the drop, which is lying at axis of symmetry. Is this point clear? So corresponding to this central position, so this is my equation number 2. Now once I apply this equation number 2 at origin, what will be happening at origin? At origin my y will be equal to 0. Okay, so if my y is 0, then Pi minus P is becoming equal to 0. Okay, but my Pi minus P from equation number 1 is nothing but equal to 2 sigma by R naught. So if for Pi minus P, the hydrostatic force, I have used my origin such that at the origin point this left hand side is becoming 0, I have to also use some other additional term in the right hand side in order to make the pressure because of the surface tension also equal to 0. Okay, so that's why what I will do in this particular right hand side, I will add one more term. So this is my 2 sigma by R naught. Now I will add one term which will give me value of right hand side equal to 0, particularly at origin. Okay, so that's why what I have done over here minus sigma by R1 plus sigma by R2, and this term is included in such a way so that at the origin I am getting nothing but my surface tension pressure because of the surface tension equal to 0. Is this point clear? So now what will be happening? The point which is lying at the axis, origin point, at this particular origin point, either if I take this plane or if I take other perpendicular plane, this plane, in both the planes I will be having radius equal to same, because this particular point is nothing but showing symmetry in the complete 360-degree direction. Okay, so any plane if I take, any two mutually perpendicular planes if I take, which are lying at this point of origin, which is nothing but the tip of the top tip of this particular drop. Okay, so in this case I will be finding that radius will be equal to nothing but the radius of curvature will be same, and it will be equal to R naught. Okay, so at this point, because at the central point the periphery of the drop is purely symmetric in all the directions, so that's why for origin what will be happening? R1 will be equal to R2 will be equal to R. Okay, so once this condition is satisfied for the origin, then my right hand side will be becoming equal to, so for origin this entire right hand side will become equal to 0. Okay, so it means that if in my hydrostatic pressure term Pi minus P, if I replace this Pi minus P with rho P minus rho times G into Y, which is nothing but my hydrostatic pressure, considering that tip of the drop is nothing but at this origin is nothing but at tip of the drop. Okay, so corresponding to this, when y will be 0, this left hand side is becoming 0. So that's why the pressure because of the surface tension should also become 0. So upon including this term, now I can take sigma as common outside, and I will be getting 2 by R naught minus 1 by R1 minus 1 by R2. Okay, so it means at the origin I have balanced now the pressures, that is hydrostatic pressure and the pressure because of the surface tension. Is this point clear? Now if I move to any other point, say in case of a pendant drop I am moving to this point number 2. Okay, so if you see the location of point number 2 is below the origin. Okay, so location of point number 2 is below the origin. It means y is negative for this case. Is this point clear? If y is negative for this case, and obviously dashed portion is representing the higher density, so density of particle here rho p is greater in comparison to the density of the surrounding phase. So that's why rho p minus rho term will be positive for this particular case. So if rho p minus rho is positive and y is negative, this entire left hand side will become negative. Is this point clear? So if this left hand side is becoming negative, now this particular term is fixed, because here radius of curvature is r0, which is corresponding to the origin. But r1 and r2 are the radius of curvatures corresponding to point number 2. Okay. Now, if my left hand side of the equation is becoming negative, then this particular right hand side should also give me the overall this second term to be dominant in comparison to the first term, which is a positive quantity. Okay. In order to dominate for the second term, the value of r1 and r2 should be, these values should be less. So it means that for a pendant drop, once I move away from the tip of the drop, which is nothing but lying at the axis of symmetry, the radius of curvature actually decreases. Is this point clear? On contrary, if I use for a sessile drop, I think I used the name pendant. So this should be for a sessile drop. On contrary, if I use a pendant drop, so for the pendant drop, what will be happening? This is my point of origin, and I am moving when away along this interface. When I am moving away from the point of origin, I am nothing but moving in the direction of positive y. So if my y is positive, density difference is positive, this term is becoming more positive. So for this term to be positive, in the right hand side, my first term should dominate. Okay, so that's why second term has to become smaller. In order for the second term to become smaller, r1 and r2 should be more or large. Okay, so that's why for a pendant drop or pendant bubble, as we move away from the point of symmetry along the interface, its radius of curvature increases. Is this point clear? So now is it clear what is the origin of this entire equation? Okay, so this is nothing but corresponding to the origin point we are actually balancing. So otherwise you will get a confusion that simply when we talk about basic fluid mechanics, then simply we say Pi minus P is equal to 2 sigma by R0. So there we are not fixing any reference, and moreover what we are saying is that at the entire outside of the drop pressure is P. So it means we are neglecting the hydrostatic part there. So once we include the hydrostatic portion and we specify a origin, then we have to include this additional term in order to balance the left hand side. All are clear with this idea? Okay, so now let us move further. Now, second situation can be, so in this previous slide, whenever I talked about the shapes of fluid particle, all the fluid particles were restricted by some solid boundary. Okay. Now we will consider a case where we have fluid particle present in the medium, but it is present in a medium of infinite size. So it means that if I consider this room to be my outside continuous medium, and inside this if a drop or a bubble is present, so that is now my fluid particle. Okay. So for that type of fluid particle, what we will be finding, we will be actually experiencing the different shapes depending upon its different parameters. Okay. So one of the shape which is experienced by the fluid particle is called as spherical shape. So when size of the particle is very small and it is mimicking the complete sphere, then we call the shape as nothing but the pure spherical shape. Okay, but this will be only true when our sizes are small. If size of the fluid particle is increasing, then there will be actually deflections in the shape. So these deflections will be reflected something like this. So here you can see the shape is not exactly spherical but something deflected. So this is called as actually ellipsoidal shape. Okay, so we have discussed yesterday in the previous lecture as well, and typically ellipsoidal shape can be specified in two further parts depending upon the aspect ratio, oblate and the provate shape. Okay, now there is one more third type of arrangement. In that arrangement, what happens here, you can see. So all these shapes are corresponding to that in the surrounding you have fluid present up to infinite portion, and all these bubbles are nothing but rising at the rising or moving down within the continuous medium at constant velocity. So uniform motion assumption is there. Okay. So now if you further increase the size, then you will be finding that you have this particular type of shape with almost the flat profile at the back. Okay. So now if you see, this shape is nothing but, if you consider a sphere and if you slice the sphere near the top, so then it will be looking like some portion of the sphere. So this particular shape is called as spherical cap shape. Okay, so this shape is nothing but a spherical cap shaped fluid particle. Then again here also one fluid particle is shown, but this one is almost close to a ellipsoidal shape. Okay, then this is another photograph of a fluid particle, and here you can see that in this particular case there was some undulation at the tail end of this spherical cap, but in this particular case this is very flat from the tail end. Okay, then we have no, at any time you consider this will be the same, because what we are saying that we are considering all these shapes to the corresponding to the uniform motion where velocity of particle is same. And the second important point, we are saying that along the interface all the tangential and the normal forces are balanced. So it means this shape will not change. If the forces are balanced, then this shape will not change. Okay. Yes, we are changing the volume of the drop. Okay, volume of the fluid particle.
So same fluid. Same fluid.
Yes. Then, in case of third, you can see this is again a spherical cap, but with some small neck at the sides. Okay. Then fourth shape is again a spherical cap, but with some volume of air encapsulated inside it. Okay, so this particular shape is called as spherical cap with skirted portion. Okay, so in the subsequent slide I will show you a detailed design map where all these shapes are actually shown. Then this is another shape. This is also a spherical cap, but it is having so many surface irregularities over that bubble. Okay, so it is having large number of interfacial waves traveling over the surface of the wave. Then all these shapes were corresponding to the scenario when you have not provided any restriction. But once you provide restriction from the sides, like you don't consider infinite amount of continuous fluid present, but you consider a tube. So what will be happening? A tube will be having finite sized diameter. So once it is having finite sized diameter, some wall effect will be coming. Okay, so because of that wall effect, if your volume of the bubble is very high, so what will be happening? This volume of the bubble will try to attain the central portion of the tube. Okay, and it will form a longer bullet shaped bubble. Now, if you say that you have a completely closed tube, and in that completely closed tube you are having some larger air volume at the bottom. So what will happen? Because of the buoyancy force, this air volume will rise above. So once volume is rising above, in a closed tube, this volume, if it is moving from the bottom portion, then of course whatever the fluid is there in the top portion, that has to occupy the bottom portion. So in order for to have that, what we will be finding, that this is rising in upward direction, and whatever the fluid it is facing ahead of this, that particular fluid will move in downward direction through this annular portion. Okay, so here bubble is rising in upward direction, but liquid is actually moving in the downward direction. Now all these shapes, whatever I have talked about, so you can see these A, B, C, D, E numbers corresponding to different shapes. So you are talking about the fluid. So here fluids are actually mentioned. Dispersed phase means fluid medium of the fluid particle, and continuous phase means fluid medium of the surrounding particle, and they are corresponding this M. So M is nothing but it is called as Morton number. What is its definition? That is given over here. So you can see Morton number is G mu 4 delta rho divided by rho square into sigma q. So this dimensionless quantity is called as Morton number. So these are the different values of the Morton number, and this is equivalent diameter in centimeters. Okay, and then this one more number I am having, which is called as Eötvös number, or its another name is bond number. Okay, so here the values of bond number is actually also given over here. So here you can see that this particular number is nothing but delta rho G into D equivalent square. So it is nothing but representing the effect of gravitational forces. So once you compare the interplay of gravitational forces with sigma, what does sigma represents? Surface tension force. So if you compare the interplay of gravitational force and the surface tension force, then whatever number we are getting, that we are calling either as Eötvös number or bond number. Okay, then Reynolds number is also there. So Reynolds number we all know, it is nothing but inertia upon viscous forces, and third number we are having is Morton number. So Morton number basically include all the effects together, viscous, gravitational as well as the surface tension. Okay, so all these three effects are actually simultaneously included in this particular number. So why only these three numbers are important? Because based on these three numbers, actually a detailed flow design map is given in the literature, based on which we can actually predict the shape of a fluid particle. Okay, so here you can see once the value of Eötvös number as well as the Reynolds number is small. So here you can see the Reynolds number is close to 1 or even close to 10. So it means either we are operating in the regime of Stokes flow or creeping flow, or very small Reynolds number. So if we are operating in very small Reynolds number regime, what will happen? Inertial forces will not be much stronger. Okay, and Eötvös number is also small over here. Okay, so in this particular region you can see the shape of the drop is actually purely spherical. Okay, once you go to the regime of slightly higher Eötvös number and the Reynolds number. So when Eötvös number is higher, what will happen? Magnitude of buoyancy forces will increase. So if magnitude of buoyancy forces are increasing, then ultimately the velocity of the bubble will be increasing. Once the velocity of the fluid particle is actually increasing, it will feel more resistance. Okay, so because of more resistance, there will be deformation in its shape. Okay, so once it is settling to this particular shape, then it is called as a ellipsoidal shape. Okay, and there is one more shape. If you go for very higher volumes where velocities are actually sufficiently large, as well as the extent of the interface will be large, so different portions of the interface will be subjected to different types of forces. Their chances of non-uniformity and instability augmentation at the interface will be more. So because of this, we will be finding that some interface waves are constantly traveling over the complete interface profile. Okay, and this type of shape of the bubble is called as wobbling bubble. Is this one clear? Sorry? No. So all these densities and viscosities are corresponding to the continuous phase. So you have to remember one important point, that when I am defining these dimensionless parameters, so the density rho and mu over here are nothing but properties corresponding to the continuous phase. And your second question is, you are saying that average or this. These are properties. Okay. So if you are considering that we are talking about adiabatic flow situation and a Newtonian fluid, then value of viscosity is actually constant. And if temperature effect is not coming into picture, then of course density will also be constant. Okay. All are clear with this idea? So what I am saying is, all these dimensionless numbers, whatever I have considered, these are nothing but corresponding to the, all the properties are corresponding to the continuous phase. Wherever I am having delta rho, so delta rho is actually this one modulus of rho dispersed minus rho continuous. Okay, so it means only density of the dispersed phase is participating. Other than that, viscosity of the dispersed phase at the moment actually we are not taking into account. Why? Because we are saying that the motion of the particle is corresponding to the static shape, single shape. Okay, so corresponding to that shape, we will be finding that the within the bubble, whatever is happening, within the fluid particle, whatever is happening, that is not coming to the interface, because at the interface everything is actually balanced. Yes, of course, when I am talking about a single bubble, so, and if you are able to, if you are zooming into the single profile and if you are able to clearly specify a boundary, then you can say that you are able to separately see the two phases. Okay. Is this one clear? Now, so this is the wobbling profile. So in case of wobbling profile, what you will be finding that all the times interfacial waves will keep on traveling across the boundary of the surface. Then we have this scale over here, which is, so this particular scale is actually log scale, and on this log scale I have Reynolds number along the ordinate, and this is also a log scale, and on this log scale I have Yudvos number, and then this side, only this particular portion I am having as log of Morton number. So this is log of Morton number, so log of m. And in this portion you can see that when my Yudvos number is high and Morton number values are given over here, in this portion you will be seeing first as a dimpled ellipsoidal cap. So dimpled ellipsoidal cap means a cap of the shape is cap shape. Then cap is also not a perfect spherical cap but a ellipsoidal cap, and then it is having small protrusions at the bottom. So this we are calling as dimpled ellipsoidal cap. Okay. Further increase of the Morton number is actually leading to shape something like this. Where you have continuous phase penetrated within that. So this we are calling as nothing but a skirted shape. And a shape which is having pure spherical cut with flat base or wavy base, that we are calling as spherical cap shape. Okay, is this point clear? All are clear with this idea? So after studying these shapes, basically what we will be doing, further we will try to see the different flow situations, and all these shapes we will also try to predict based on the mathematical analysis. That if we solve governing equations, then how a governing equation is actually helping us in generation of a particular type of shape. So that we will be seeing in the subsequent discussion. Okay. Now one important point you have to keep in mind. So we can take two important more properties. One is density ratio. So density ratio is density of particle to density of the continuous phase. This is density ratio, and K is another parameter which is mu p by mu. So here viscosity of particle by viscosity of continuous phase. Okay. So you have to keep in mind that this entire plot, whatever we have obtained here, viscosity of the particle phase has not come into consideration. Okay. But one important point we need to keep in mind that this particular curve is not applicable for extreme values of density ratio and viscosity ratio. By meaning of extreme value is, if I say that my mu p by mu is infinite. So what is the meaning? If your particle is a solid, okay, so if your particle is a solid, in that case you will say mu p by mu is infinite. So this curve is not applicable for that particular situation. Similarly, if your particle is a solid, you will find that your rho p by rho will also be very, very large. Okay, so then also this curve is not applicable. So it means that when we are having extreme values of these two parameters, then this particular curve is not valid. This is valid only for the moderate values of the rho p by rho and mu p by mu. Okay. Okay, now what we do when we talk about the governing equations, we also majority of the time try to solve these governing equations in non-dimensional form. Why non-dimensional form? Because in dimensional form, if you do the analysis, then what will be happening? For each and every case, you have to do experiments or do simulation or theoretical trials. Okay, but if you try to non-dimensionalize the equations, you will be finding that a group of parameters will be clubbed together in the form of some dimensionless quantities. Okay, so it means if the group of variables are clubbed together, it means that the dimensionless quantities will always be resulting in lesser number of equations or lesser number of parameters in comparison to the actual number of parameters associated with the flow situation. Okay, so that's why majority of the time it is kind of particularly whenever we are doing the whether you do experiments or whether do you simulations, because in case of experiments, if you do multiple cases, of course time in both cases is important, but at the same point of time cost will also be involved. Okay, if you do simulations, then you have limited computational power. Okay, so you cannot do cases for infinite number of parameters and conditions. Okay, so that's why non-dimensionalization is important. Okay, so if you consider three non-dimensionalization parameters, one is u naught. So u naught, if you say, it is nothing but your reference velocity. Okay, similarly L you consider as your reference length, and P naught if you consider as reference pressure. So if you consider these three reference quantities and then try to non-dimensionalize all the lengths, say I say my x dash is nothing but x by L, y dash is y by L, z dash is z by L. So x, y, z parameters I have now shifted to x dash, y dash and z dash, which are nothing but corresponding non-dimensional quantities when I have non-dimensionalized this with length scale L. Okay. Similarly, all the velocities, I will be having say three velocities u, v, w in dimensional form. If I non-dimensionalize this with u naught, this also with u naught, this also with u naught, so ultimately I will be getting a velocity vector, say I am calling this as u dash, v dash and w dash. So then my this bold u dash is nothing but a velocity vector in non-dimensional form. Okay, so once we perform this non-dimensionalization, this is a basic fluid mechanics thing, so that's why I will not do here mathematically, I will simply explain you the equations. Okay, so if I apply this non-dimensionalization on my continuity equation, then I will be getting continuity equation for incompressible flow as delta dash divergence of u dash equal to 0. So this is for steady incompressible flow. Okay, where my delta dash is nothing but del by del x dash I cap plus del by del y dash j cap plus del by del z dash k cap. Okay, is this point clear? Similarly, this is my original momentum equation. If I apply this non-dimensionalization on this momentum equation, then my dimensionless momentum equation will become d by dt dash of u dash minus gradient of pressure Pm. Pm over here is nothing but, we call this as modified pressure. So this is a dimensionless pressure and this is a modified pressure. And then with the viscous term, we get one term which is 1 by Reynolds number, where your Reynolds number is nothing but equal to rho L u naught by mu, and this mu by rho you can write. Is this point clear? So this is my non-dimensional form of momentum equation. This Pm dash is important quantity. So one important thing you can see, when I have gone from this part to this part, so these two terms are combined together into a single term called as modified pressure, and this replacement of this term is my this particular term. Okay, so now here you can see this modified pressure Pm dash is given as P minus P naught, where P naught was some reference pressure, minus rho g HV divided by rho u naught square. Okay, so this is the value of this Pm dash. Now one important point is this modified pressure is also having some physical significance. Okay, so if you see in my original equation, this pressure was nothing but hydrostatic pressure. So when I am going from this point to this point, then it is doing the negative of hydrostatic portion over here. So it means that this modified pressure is representing the only pressure which is coming because of the fluid behavior. It is not accounting for the hydrostatic portion, because that I have already taken as negative from this point. So this is the relevance of the modified pressure. So what does modified pressure reflects? Here also the kind of referencing we have done while specifying the drop shape, like we have set our origin corresponding to which my hydrostatic pressure was becoming 0. Similar way here also, once from my total pressure I am taking out the hydrostatic portion, then whatever left in the pressure is actually only quantity of pressure because of the fluid flow, so which is connected because of the fluid motion. Okay, now up to this point, is it clear? HV is nothing but the direction which is height which is measured in vertical direction with a reference point. Okay, so HV is height measured in the vertical direction. Now when we will be applying these equations to our multi-phase flow situations, of course, whenever we solve the partial differential equations, all these are nothing but the partial differential equations. Okay, so when we solve the partial differential equations, what we need to do, we need to apply the boundary conditions. Okay, so some of the boundary conditions are common, which are already known to you. So if you have a domain, then at walls you specify that tangential velocity is equal to 0, which is nothing but a no slip boundary condition. And if it's a solid boundary, then normal velocity is equal to 0, because it's a impermeable boundary. Okay, then pressure also you simply supply the values, either you give Newman type boundary condition for pressure, or you give some specified known value of the pressure. Okay, so this type of boundary conditions are almost clear to us, that if I have a domain, fluid domain, and if fluid domain is interacting with the solid boundaries, Okay, then what type of boundary conditions are to be supplied, that is almost which is known to us. But if I consider that I have some particle which is not at the outer walls, but it is within the domain. Okay, so here what will be happening? This is my one outside phase, this is my continuous phase, and of course this particle can be a solid or it can be a fluid. But in between this solid or fluid particle, I will be having this interface. So at this interface also different types of kinematic and dynamic boundary conditions will be actually acting. Okay. So if this is a solid particle, what will happen? The tangential velocity at any solid particle is always equal to that of the velocity of the solid particle. That is something which we know from no slip condition. What does no slip condition means? If you have any particular boundary, parallel to that boundary fluid velocity will be 0. So for solid particle, if I ask, all of you will say that tangential velocity, any tangential velocity will be nothing but equal to tangential velocity of the particle. Okay, so tangential velocity, this left hand side is representing the velocity in the continuous phase. So tangential velocity in the continuous phase will be equal to tangential velocity in the tangential velocity of the particle. Okay.
Vertical sides air.
Yes, now I am coming to other point. Okay. Now you can take another example. Say you have a lake of water, and that particular lake of water is having actually stagnant free surface, and air is flowing over that lake of water. What will happen to velocity of air particle which is just adjacent to the water surface? It will be 0, corresponding to the, so it means that whatever the no slip condition we tell, though in our basic fluid mechanics course always we nothing but refer to the situation of a solid boundary, but it is applicable for any other type of boundary as well. So that's why whether my particle is liquid or it is air or it is solid, every time this tangential velocity boundary condition will be satisfied. Okay, so at the interface, you have to remember this point. I am not saying that tangential velocity of this total particle. I am saying tangential velocity of at this boundary of the particle, at this interface of the particle. Okay, so whatever the tangential velocity at the interface of the particle is there, for the particle phase, same will be tangential velocity for immediately outside continuous phase. Okay, and this particular condition is coming nothing but from the no slip boundary condition. First point is clear. Now, second important point, if a solid particle I am having, we know that solid particle is a rigid particle. Okay, so if solid particle is rising vertically upward with some normal velocity un, of course whenever it is rising upward, what I will be considering? I will be considering velocity of the particle which is normal to its boundary. So normal to interface, whenever a solid particle is rising, then whatever the immediate fluid layer is there, that will also be carried forward with the same velocity, okay, because of the adhesion. So that's why I am saying that normal velocity is equal to normal velocity of the particle. Now same situation is also true for fluid particles as well, because if you have a fixed volume of particle, what you have? Fixed volume of particle, you can say a fluid particle, and you are saying that you are doing your analysis under the equilibrium conditions such that the shape of the particle is not deforming, or even if shape of the particle is deforming, then also whatever the normal deformation or normal motion you will be finding at this point, same normal motion will be actually conveyed to immediate outside fluid. So simple thing, if say you have a balloon, okay, if you press the outer boundary of the balloon. So once you are pressing the outer boundary of balloon, it means you are giving some normal velocity. So outside the balloon there was some air, that air will also move in the normal direction. At the same point of time, whatever the inside fluid is there inside the balloon, that will also immediately air. Of course, at larger distance away from the interface, fluid will move here and there, but immediate next layer, which is just adhered to the boundary of the balloon, that will also move in the normal direction with same magnitude. So that is what I am saying, that this is coming, that normal velocity in the continuous phase at interface. So all these boundary conditions, both of these boundary conditions are nothing but acting at the interface. So normal velocity in continuous phase will be equal to normal velocity of the particle, particularly at the interface. Away from interface, particle can have any other velocity. Is this point clear? So these two are the kinematic boundary conditions. Then we must have some dynamic boundary conditions. Okay. So when we will be talking about the dynamic boundary condition, of course we have to balance the forces. Okay. Forces means we have to balance the interfacial forces. What are the forces which are acting at the interface? So at the interface, there will be some force which is always acting normal to this. Okay. If this is acting, and of course from inside also there will be some force in the normal direction. So the normal force from inside is pressure of the particle. Normal force from outside is pressure of the continuous phase. The difference of these two pressures will be equal to surface tension force if and only if my particle and surrounding phase are at rest. Okay. But if I say that this particle is moving in the surrounding continuous phase, then there will be some relative velocity in between the particle and the surrounding continuous phase. So because of that relative velocity, there will be some shear stress also in the tangential direction. Okay. So that's why whenever I will be writing the total force balance, I have to also account for shear forces. Okay. And whenever we talk about the shear forces, particularly in Newtonian fluid, we have seen two types of forces. Like when we write the complete Davionic stress tensor, then we have normal stresses as well as the shear stresses. Okay. What are the normal stresses? In x direction, normal stress is 2 mu into del u by del x. In y direction, normal stress is 2 mu into del u by del y, del v by del y, and 2 mu into del w by del j. So these are the normal stresses producing because of the viscosity. Okay, because of the viscosity. So now we will be having normal shear stresses. So normal shear stresses will also act normal to the boundary. Is this point clear? So these will act normal to the interface. So this is tau and n, nothing but represents the normal stresses in the particle, and this is normal stresses in the continuous phase. And these two normal stresses are contributed because of the Davionic stress tensor. Davionic stress tensor means because of the viscosity, and these will be coming only into play once you have motion. Okay, if you don't have motion, then these will not be coming. Yes, so there you will not experience this. Okay. Now, the way we have balanced the normal force, and also we know that this normal pressure is nothing but balanced by the surface tension force. So that is my first boundary condition. So this first dynamic boundary condition is actually balancing the normal. This is balancing the normal to interface forces in direction normal to interface. Now I will be having some forces along the tangential direction to the interface also. Okay, because when I have talked about the Deviatric stress tensor, it does not give only normal forces, but it also gives the tangential forces, shear forces, and majorly the major magnitude comes in terms of shear forces. Okay, so that's why this tau nt is shear stress in the continuous phase, minus tau nt is shear stress in the particle phase, and these two shear stresses will be balanced by the tangential force because of the surface tension. Okay, so how tangential force will be coming because of the surface tension? If you consider that this is your interface, if say at this portion of interface your value of surface tension is sigma 1, then at some next portion of interface its value is sigma 2, then it is sigma 3, sigma 4. So likewise, whenever you are moving along the periphery of the interface, if along the periphery of the interface gradient of the surface tension is existing, then only you will find a force in tangential direction because of the surface tension. Is this point clear? So tangential force will be only coming if you have gradient of surface tension in the tangential direction. So it means all these shear forces will be equal to this gradient of sigma term, and this particular gradient is nothing but this is applicable at the surface of the particle. So it means it is only acting at the interface. For all scenarios, so basically what happens, a small amount of contamination of the interface leads to different values of surface tension at different portions. So if dust particles or any other thing gets collected at the interface, that actually modifies the surface tension force. Okay. At the same point of time, if you have temperature gradient present in the system, so this surface tension at the interface can be modified because of two reasons. One is because of the presence of the surface contaminations or surfactants. So if you say that surfactant concentration is different at different portions, then you will be having different surface tension depending upon the surfactant concentration. Okay, so surfactants or any other contamination basically decreases the magnitude of the surface tension force. Second point is there can be variation in surface tension because of the temperature effect. So typically if you consider water, okay, water is nothing but immiscible with air in the normal atmospheric conditions. If you start heating water and say at atmospheric pressure condition, if you have heated water above than 100 degrees Celsius, what will happen? All liquid molecules of water will convert into vapor, and now the vapor form of the water is actually miscible with air. So once you have entire water converted into the vapor, now in between the water vapor and the air you cannot define a definite interfacial boundary. So it means interface is lost. Once interface is lost, it means surface tension force has become 0. Surface tension coefficient sigma has become 0. So it means that at low temperature surface tension coefficient is high, and as we increase the temperature of the liquid, then value of surface tension coefficient decreases. And particularly at critical point, after the critical point entire liquid will be into the vapor phase. So above critical point value, at critical point value is 0, and above that of course it will be 0. Okay, so at critical point or above critical point value of surface tension coefficient is 0 because we don't have presence of any interface above that. Okay, so if you have any system where you are saying that you don't have any surface contaminations, if you don't have any surface contaminations, then this gradient of sigma will be equal to 0. Once this term is equal to 0, it means that shear stress in the continuous phase must balance with shear stress in the particle phase. Is this one clear?
सर एक पार्टिकल उसमें डिफरेंट सरफेस टेंसर हो सकते हैं.
Yes. At its different portions of the interface, there can be different surface tension.
So, and this tangential force of surface tension will depend on the surface area.
Yes, yes, yes.
मैं पूछ रहा था कि एक सिंगल फ्लूइड पार्टिकल के लिए सिग्मा अलग अलग हो सकता है.
Yes, say you have a fluid particle, you have seen that some dust particles have entered into the flow and these dust particles got collected at this portion. So this portion will be having low surface tension, top portion will be having high surface tension. You can have another situation. You have a heating scenario and this bottom portion is at high temperature and top portion is at low temperature. Gradient of temperature, gradient of surface tension. Okay. So if your temperature gradient is not existing or there is no contamination of the interface, then gradient of this surface tension will be equal to 0. So once this is 0, then my tangential force in the tangential stress in the continuous phase will be equal to tangential stress in the particle phase. Is this point clear? So all this gives nothing but the detailed set of boundary conditions including kinematic and dynamic boundary conditions at the interface between the two fluids. Two fluids or solids. One important point, if you have a solid particle, then only velocity boundary conditions will be there, because within the solid particles there will not be any pressure or this shear. Okay, because for a rigid solid particles, if relative motion between different portions of the particles is not there, then these two boundary conditions are not at all needed. Okay, because particle we will be considering as a single point moving in the flow field. Within the particle there is no motion, so that's why there is no interest, there is no shear stress and no pressure because no fluid is within the solid particle. So if you have solid particle, then only these two conditions will be sufficient. But if you have fluid particle, then you have to include the complete set of conditions. And whatever the conditions I have given you, these are the most generic one. Now, whatever situation you will be actually taking further in your analysis, there some of the terms may vanish. Okay, depending upon the different flow situations. Is this point clear? So this is a typical representation of extension of this particular first equation, and this extension is actually presented for a axisymmetric flow situation. So if you have axisymmetric flow and the particle is actually having radius equal to a, then if you have a spherical particle of radius a, then right hand side will become 2 sigma by a, and in axisymmetric scenario, so pressure will be remaining as it is, but whenever you will be talking about the normal stresses, so normal stresses will only be present in the which direction? Radial direction for a particle. So that's why this is the normal stress because of the viscosity in radial direction for particle, and this is normal stress for continuous phase. Is this one clear? And once you write this second term, so for second term, for an axisymmetric particle, the gradient will be only, gradient of surface tension will be only existing along the theta direction. So that's why 1 by a d sigma by d theta. So this is the gradient term, and then shear stresses, if you talk about, these will be nothing but in r theta plane. Okay, so here you have mu p times, so these are representing nothing but the corresponding shear stresses in particle and the yes 2D axisymmetric assumption. So what you need to do in the next lecture onwards, we will try to see the analysis of this type of system for different flow situations. So when we will be doing the analysis, of course, initially we will be starting with the more simplest assumption, that is nothing but a spherical shape. Okay, and considering the spherical shape and appropriate use of coordinate system, majority of the analysis we will try to do in the spherical coordinate system. So that's why what I suggest you people that please revisit your governing equations for cylindrical and spherical coordinate system. So you need not to do the derivation. Of course, majority of the time, whatever the analysis I will be doing here, I will also not do the complete derivation. We will more try to take the physical inferences with the final results. Okay. So what I suggest is please revisit your governing equations for cylindrical and spherical coordinates, continuity and momentum equations, particularly for the Newtonian fluids, so that whenever, depending upon the different assumptions, we are removing some of the terms, you should actually be able to understand that idea. Okay.
सर ये यूपी वहाँ पे होगा, यहाँ पे होगा,
Where?
ये नीचे सर
This is mu p, na?
पार्टिकल के लिए इस तरफ होगा ना.
See, you can put it any side depending upon the sign of your these. It may happen that both of these are of negative sign. That's why this has actually gone to other side. Okay. So depending upon the system, your sign can be adjusted. Fine.